All right, so we're going to get started here. Thanks everyone for joining us today. This is the first in the Complexity Science lecture series. I'm Mike Norman. If you have any questions, feel free to follow up with me, and I'll do my best to answer them. I'm the Applied Complexity Science Capability Lead for the Systems Engineering Technical Center. So real quick, I just want to talk about why we're here. So why are we here? Because, from a high level, complexity science is the study of emergence, right? This emergence is driven by decentralized decision making. Applied complexity science is an attempt to leverage the discoveries of complexity science to design or modify complex systems capable of producing non-pathological emergence. It's a big statement there. But basically, by using generative computational methods like agent-based models, we're able to take a coarse-grained perspective on a complex system of interest. And by using artificial intelligence agents, such as reinforcement learners, we can take new approaches to developing decentralized rule sets and policies for individual decision makers that they can follow, which will enable the desirable emergent functionality and avoid the pathological kind. But today we're going to start things off here with some of the implications of complexity science for modeling, specifically in the statistical sciences. So I would like to. It's my pleasure to introduce Harry Crane. I have his bio here. I'd like to do it justice. So, Dr. Crane is an associate professor and co-director of the graduate program in statistics and biostatistics at Rutgers University. Before Rutgers, Harry received his PhD in statistics from the University of Chicago and a BA in mathematics and economics from the University of Pennsylvania. He has previously held positions as a visiting scholar in mathematics at UC Berkeley, a research associate at the RAND Corporation, and research fellow at the Foreign Policy Research Institute. And so Dr. Crane is here to share with us some of his latest work with his talk titled Complex Data Analysis, the Replication Crisis, and Prediction Markets.
Okay.
Thank you.
Thanks. Okay. Thanks, Mike. Do you
let me switch.
the slides up? Okay.
Yep.
Well, yeah, thanks for the introduction and thanks for having me. It's and I think this seminar series sounds like a great idea, and I'm glad to be part of it. And as Mike mentioned, I'm a statistician, and so I'll be talking here today a little bit about how ideas from complexity science and the understanding of complex systems figure into some problems in statistics. But I'll also go a bit beyond beyond that. I don't want this talk to be focused just on statistics, as I know that probably most people here aren't statisticians or interested in other things. But somehow these ideas all kind of come together, and so I have broken up the talk into three parts. I'll talk at the beginning about some technical aspects, technical challenges in statistical analysis that arise in the analysis of what I call complex data, and in particular about trying to do statistical inference and data science in a setting where we're working in a complex setting, so where we're trying to gain some kind of insight about a complex system, and how some of those challenges, differ from how those challenges kind of affect the tools that are available to gain insights in those situations. In the second part, I'll talk a bit about. I'll talk a bit more conceptually about how complex systems can be used for harnessing these emergent properties, and I'll be talking in a specific context of the replication crisis in science, which is certainly a situation that statistical analysis figures into, but it's much larger than that, and it gets at more of a big picture view of what I think some of you are probably thinking about with complex systems and complexity science. And then finally, I'll talk about a practical project that I'm part of, which is called Researchers 1, which kind of takes some of the ideas from the second part in how take some of the ideas from the second part and actually puts them into practice. So this is a very wide-ranging topics here, from technical through to practical, but I think that it's important to appreciate all parts of the problem in order to really see what their impact could possibly be. So in the first part, I'm going to talk about some of the more technical challenges, and I'm not going to go into in-depth mathematical detail here, but I hope to at least give you an appreciation for what I'm thinking about and what I have, what I'm working towards. And so to start off, I start off with this analogy, which is that I'm unable to read or speak Greek, and I assume that's true of most of you here, but that somehow we're still able to understand the philosophy of Aristotle if we were to be given a proper, a good enough translation of it. So it has to be somehow a faithful translation of his work. And how this relates to my work in statistics and in data analysis is that when we think about analyzing data, what we're doing is we're taking something that we observe in nature. So there are events that occur in nature, and we somehow have to translate it into a language that we can understand and a language that we can work in. And typically, nowadays, that involves some kind of computer language or some kind of framework that can be implemented into a computer so that we can manipulate and analyze these data sets. So it's understood that it's better to read something in its original language. There's always something that's lost in translation, and the same goes for data analysis. When we observe, when climate scientists model hurricanes, they do it by simulating processes on their computers. There's not actually a hurricane happening in their computer, right? But there's some kind of model for the important parts of that system that allows them to draw, hopefully worthwhile and meaningful inferences from from what they're doing on that computer. But this can, of course, but this isn't always the case. Of course, this depends on how well those models represent the system that's trying to be studied, right? And so one of the things that it seems obvious, if you have a bad translation of Aristotle, you're certainly going to have a bad interpretation of his work. Even if you have a perfect translation, in some cases, there's always things that you're going to miss. There's context that can't quite be captured and that's lost in translation. And how this relates to analysis of complex systems is that in a lot of cases, at least in the way that statisticians and a lot of, I think, network scientists are approaching problems in the realm of network science or complexity science, is working with a framework that doesn't quite properly represent these systems that we're studying. Okay. And so for another analogy, for those of you who aren't statisticians, this maybe you can appreciate this in the way that, in really the way that these statistical tools are quite limited when we get into the complex domain, which is that we all know that biologists, astronomers, scientists, they have various tools that they use to study the systems that they're interested in. And they themselves are interested in some specific kind of complex system. Biologists are interested in biological systems, which are, of course, complex. And they know that in order to study different aspects of the system, it's beneficial to have different instruments, different kinds of microscopes, or different kinds of telescopes in the case of the astronomer. So when these scientists use these different instruments, they know that they're not, so when an astronomer uses an X-ray telescope, he knows that he's not going to see the same things as if he used a gamma ray telescope. And that's taken into account when they draw conclusions about the system. Statisticians and network scientists, by and large, are using one predominant language to study complex systems, and more generally to study networks, which is the language of graph theory. So there's an overwhelming majority of the work that I've come across in the study of networks is framed as a study somehow of graphs and random graphs in the case of statistics. And what I hope to at least emphasize here is that there's a difference between, first, on the one hand, a mathematical object and a mathematical representation, which is a graph, and a specific instance of a complex network, which is, we might think of as a network, or a complex system, which we might think of it, which we might represent as a network, and then general complex systems, which, of which networks are just one special case. And so, with that, I'd like to talk, try to emphasize the distinction between what is what is typically covered and typically thought of as classical statistics, and what, how statistical ideas could be used to gain some kind of type of insights into complex systems, but the extent to which the classical picture is limited for this purpose. So if you've ever taken any kind of statistics or probability course, you've probably come across the concept of a coin, a fair coin or a coin toss. And at some level, it may sound like trivializing it a bit, but it's actually not. It's actually not. I mean, if you look at it from a certain level, almost everything that we currently do in statistics really emerges from this idea of a coin toss. So you toss a coin once, you have one outcome. You toss a coin 1,000 times, you have a sequence of random variables. That, of course, can get generalized and has been developed in various directions for to a very useful purpose. And so there's now, of course, time series, spatial statistics, and all kinds of tools that are out there that are useful in solving and addressing various problems in the sciences. But the thing that all of these methods have in common is that they're primarily framed in a setting where the structure of the data is relatively flat. So in the example I gave, I tossed a coin 1,000 times. I generated a sequence of 1,000 observations. More generally, we might have a set or a table or some kind of rectangular array of usually numbers, but not necessarily numbers, but a rectangular array of data. And the way that these models are set up is usually they're assumed to behave some kind of regularity condition. So we toss a coin 1,000 times. We have 1,000 statistically identical copies of the same process, and it's assumed that they're independent of one another. And so not only are we observing the same exact thing every time, or a result from the same process every time, but we're also assuming that these things don't interact with one another, don't affect one another. And those are appropriate assumptions in a lot of cases. That regularity leads to a very rich mathematical theory, which is all well and good. And nowadays, if you've heard of the work being done in big data, a lot of the work being done in big data, and even in a lot of machine learning, is still well within this domain. They're still aiming to use pretty much the same techniques and the same ideas. The data is still flat. It's just bigger. And it might be so big that it can't fit into the computer that they're working in, and that certainly is a challenge. But if it could fit, it would look the same. It would just be bigger. And so the major challenge here is in scaling up existing techniques, and that's a computational challenge. When we get into the complex domain, the challenges are more conceptual in nature. The data doesn't need to be very big at all to make the problem very difficult, and that's because what makes these problems interesting and what makes them difficult what makes them complex is the structure in the problem, and it's what I would call depth, but the idea that there are many different aspects of the system and they're all interacting with one another, and we can't just isolate one part of it from the rest and study that part without affecting the rest of the system. And so this leads to what appears to be irregular behavior, at least irregular from the perspective of from a traditional perspective, for which there's very little theory. But more importantly, from my point of view, it leads to structures that just aren't well suited to be handled from the traditional point of view. Okay? If we take a complex system and we represent it as a sequence of observations, we're necessarily losing a lot of structure. And so, in order to approach these problems, what I'm working towards and thinking about is, how can we enrich the framework so that we're actually able to better express these systems first and foremost before we can get into any kind of drawing any kind of conclusions about them. And one more thing I want to say about this is, I talk about networks a bit, and I don't want to conflate a network with a complex system. I see whereas I use the idea of coin tossing as kind of the base case of classical statistics, and actually from the point of view of classical statistics, classical data analysis, networks are kind of the limit right now. They're the upper limit. That's what we consider to be the most, they're posing some of the most challenging questions. From a complex data point of view, networks, I think, are the equivalent of coin tossing. So a network is typically represented, we have nodes and we have connections between the nodes. But in a complex system, there are many other possible interactions between the interactions, and so on and so forth. Much higher order structure that we're not really even in a position to think about, or even in a position to express formally, let alone deal with. So, with a couple minutes, I want to illustrate how this manifests itself in practice with one quick example. If you've encountered any kind of work in networks, at least in the current day, one of the main interests is in dealing with networks that have a common, what's called scale-free or sparse or heavy-tailed structure. Okay. So the idea is that a lot of networks that are of interest now, things like social networks, the internet, and other things that people are studying. I have here a few plots of that I'll talk about in a second. They have the tendency to have relatively few edges. So every person, people who are, if you're talking about a social network, each individual person tends to have very few social connections, on the order of maybe 5 or 10. And yet people are somehow very well connected, and that's because even though most people have a very relatively low degree being the number of connections to other nodes, there are still people with very large degree, and that's what gives this network a very what's called a heavy-tailed structure. So even though while there are very few edges, the network is somehow well connected by these high-degree nodes, and that's this heavy-tailed structure is typically demonstrated through these power law type plots, which this is a plot. This isn't necessarily intended to be readable, but as you can see, these are all trying to show the same thing. These are plots on the log-log scale, so I have the log of the degree on the x-axis, the log of the proportion of nodes with that degree on the y-axis, and power law is when you see this kind of negative linear relationship on that scale. Okay, so those are empirical properties that we think, these are very basic properties that we think that we see in real-world networks. And so they're properties that a good statistical inference would take into account.
Can I just ask?
Yes,
please. I was
please.
a little bit confused by it. You're saying that the well-connectedness comes about from the low number of vertices with large connections, or just even if all of them have only 5, that still results in well-connectedness? I didn't know when you mentioned the low number, or something like the low number of high-degree nodes.
I don't want to make a causal claim here, but what I would say is that it seems to be that I only know a very small number of people, but I can somehow know people this 6 degrees of separation idea. What's actually driving that phenomenon? At least part of it seems to be that there are parts of this. There are these high degree nodes that are connecting these otherwise distant parts of the network. That's all I was trying to say there. Is that?
Yeah, I just wanted to make sure that you're saying that was the key thing.
Yeah, I think that's the key.
It would have that the large number of degrees separation would happen even without those.
Oh no, I don't think so. No,
Okay.
and I guess part of this power law structure is that while there are relatively few nodes with these high degree properties, it's relatively large compared to kind of it's heavy-tailed in the sense that the proportion is relatively large compared to other distributions that it could be.
So you're saying there are a few people that are very well connected, and that kind of allows there to be only 6 degrees of separation.
Yeah, I mean, this is the idea of, so there's a few people that are very well connected to kind of diverse parts of the network that otherwise wouldn't be connected, and they're kind of holding a lot of things together. So these are called hubs or things like that.
Kim Kardashian.
Okay.
Exactly. Yeah. Exactly.
So empirically, what we see is these kind of what at some level is an irregular, some kind of inhomogeneous behavior in the structure of the network, and how this poses a challenge statistically. So what we want to do in statistics and in any kind of data setting is we want to observe something and then make inferences about things that we didn't observe. We want to draw inferences from a sample to a population, for example. And in order to do that, this is kind of a fundamental aspect of inductive inferences, is that in order to connect past to future or observed to unobserved, there's some, we need to make some, we generally need to make some assumption about how the observed is related to the unobserved, how the past is related to the future. And that requires some assumption of regularity in the system. We need the part that we see to be similar, at least in some ways, to the part that we're trying to draw inferences about. Usually when we introduce these, so these come in the form of assumptions in statistical models, but these assumptions, I'm not going to talk about exactly what they are. The kind of the key word here is exchangeability in a lot of cases. These assumptions impose a lot of regularity into the system, so it kind of ends up washing out or contradicting what we observe to be, or some irregularity that we might observe, and so it leads to, while kind of logically the models are coherent, what they do, what it ends up doing is they might be coherent, but for drawing inferences about a system that's nothing like the one that we're actually interested in, and so this reminds me of a quote from a famous statistician, George Box, who's well known for saying that all models are wrong, but some are useful. And there's an extent to which, of course, this is true. But this gets taken a little bit too far, I think, by a lot of statisticians who, if their models are criticized, or if you say, well, your model doesn't do this or your model doesn't do that, they fall back on, well, yes, but all models are wrong, missing the part that that while that's true, there's this last part that's only some are useful. And what is it that makes a model useful? Is what I'm trying to get at here. And so I'd like to at least update this to say that, all models are somehow wrong, but not all models are necessarily rightly to be considered models, right? In the sense that they're not actually modeling the thing that we are interested in. And that certainly is the case in the context of network analysis, and I have an example on the next slide.
So what are some of the examples of usefulness that looking at these networks comes through through a complexity lens? I don't know much about complexity, that's why I'm here. That you said that these networks have heavy tails. Well, what are some useful insights that you get as a result of that model? That complexity theory can
Well,
give?
you could answer that with a marketing solution, which is if you find the influencers in the graph and you get them to promote your product, you could have the most impact with your advertising dollar.
So the insight is you should market people who have a lot of links. I mean, you don't need mathematics for that.
Well,
but you did need to understand the structure of the network.
Yeah, the effects of diffusion in a network that's structured that way are different than if it isn't structured that way.
Yeah.
Yeah, I mean, I think that the purpose of these mathematical tools is that example might seem to make perfect sense without math. There's a lot of examples where you might think where we do derive maybe some counterintuitive observations, or something like that ought to be tested at least, and that's one of the purposes that these
How about
models
a different one, which is the critical point at which a nuclear system will explode. That's a standard statistical property, right? But it results in a step function in behavior.
Right. So that's
what your
this
point is.
phase transition.
Yeah,
in
your
that
statistics
case.
model your population, whereas in these kind of systems with parallel behavior, one element way out of the tail can be the most influential.
Right, and I guess what I should say, as a statistician, I know that many of you have other perspectives, is that I'm not necessarily interested in this power law property, but I'm trying to maybe draw inferences about other aspects of the network. But in order to trust the inferences I get from a model, I hope that my model should at least replicate parts of the system that I believe to be there, that we observe in the data, and that's we're actually at that level here. We're not even we're not even beyond that at this point. So it's
So if you use a random graph and your thing is heavy tailed, any conclusion you make is basically, certainly is more likely to be invalid because you haven't captured something that is maybe key to.
Yeah, I would say there's not much reason to trust that model, right? And this is the example. This is an example that I have here that I won't. I don't want to dwell on this because I want to get to the next part, which is, there are models that people are studying and that are very well studied in the statistical literature that basically, if I have a network and I'm interested in analyzing it, so I have something with links, there is structure to it, but I fit these models to it. So if I have, I guess the point is that if I have if I observe a part of a system that is believed to be sparse, so it's believed to have the sparsity property, or if it does have the sparsity property, but I nevertheless actually observe a non-trivial piece of it, then if I were to fit something like a random graph to it, as soon as I fit the model to it, what does that model tell me? Well, it tells me, or it implies that with very high probability I would have observed an empty graph under that model. But by the nature of actually entering into this problem, I'm dealing with something that's not empty. I wouldn't want to analyze something that doesn't have any structure to it. So the model, kind of automatically refutes itself as soon as it's being fit to the data. And so it's not to say that a conclusion drawn from it is wrong, of course, but there's no necessarily reason to trust it, right? So one of the things one suggestion, and I don't claim to have the solution to this, I'm working towards one, and I've talked about these ideas in a book of mine recently, which is that if we're studying networks, we're interested primarily in structure. And what drives structure, and at least the examples that I'm talking about, is the interactions among the different elements of the system. And so this is what I call a structural paradigm, in which why I think the graph theoretic way of thinking about networks as random graphs, or modeling them as random graphs, is insufficient. Isn't necessarily that any one of these models is bad. I mean, I think they turn out to be bad for specific applications, but it's that they take a very specific perspective on the system, which is from the perspective of the vertices. A graph is defined mathematically as a set of vertices with a relation on those vertices. So the vertices are somehow the primary component, but in a complex system and in a network, it's actually the interactions that drive the structure. And an example of that would be an email network or a phone call database. I won't get into this example, but I just want to call some attention to what seems to be a very simple fix or a very simple change, although it took a while to figure out. If instead of representing a network as a graph with from the perspective of vertices, we look at it from the perspective of edges, and we represent these things as, possibly as edge-labeled graphs, if you want to think of them that way. Then we are able to actually, we are able to get kind of coherent statistical models that also replicate these basic empirical properties. So that's at least one benefit of this alternative approach. I should point out that while this picture here of an edge-labeled graph looks like all I did was take the labels from the vertices and put them on the edges, I mean, that's all that the picture does, of course, but mathematically these are actually very different objects to manipulate, and that's at least has something to do with what allows us to maybe address these problems from this different perspective. From a bigger picture point of view, I think this gets us moving in the right direction. I mean, I don't suggest that all networks are appropriately modeled in this way, but at least it gives us the insight that there is benefit to looking at systems from a different perspective. This is a different perspective. It allows us to see different things. Back to the telescope example, and we want to move even more in this direction, and that's what I am working towards as part of a bigger, much longer term project. I think it's 5, 10, could be 15 years down the line. I mean, in order to work in this, in order to appropriately account for structure, we have to think very deeply about how we're even expressing these kind of logically and encoding them into a computer so that the structure is faithfully represented. And so that's not something that I can really talk about today, but more information on this can be found. I talk a lot about these problems and the state of affairs as of today in this book, and I hope that down the line there will be more progress in this direction. So I'm going to move on. Is there any quick questions before I move on? Yes.
I don't understand the big question that you're solving. What's the problem that statisticians are getting wrong that you're going to help fix?
Well, there is no. If you're asking for a big problem in the sense of a real-world problem, we're not even we're not even in a position. What I'm saying here is we're not even in a position to adequately address real world problems, because whatever tools we have are, they're for all intents and purposes bogus for the applications we're interested in. They're not going to give us. They're not representing the systems that we're trying to study. As far as what the actual problem is, so statisticians are working on things like, I guess advertising. They're working on things like, they may not be working. There are some working in cybersecurity, spread of disease or infectious disease on networks and things like that. So these are inferential problems. When we study the spread of a disease, as a statistician, my job isn't to say anything about the people who already have the disease. That's already done, right? But I have to give, I want to draw some inferences about, given the state that the system is in, where is it likely to spread and how can it be possibly stopped? In order to do that, we need to actually have a proper rendering of the system that we're actually trying to intervene and to work on.
And you're asserting that things aren't being done well with spreading of diseases?
Well, I'm asserting that we need to model the network. If we want to model these as networks, then the network structure has to be proper. That has to be modeled in a more in a more accurate manner. I mean, there are other examples, but I am saying that at least these properties that people are primarily, I highlight these two very basic properties, not because they're the be-all and end-all, but because it at least highlights that from a fundamental perspective, what does it mean to model a system? If we model these systems, we don't want to. We're not interested in properties of the system that we already know about. But if we're modeling the system, in order to, at least from my perspective, in order to trust the model on things that we don't already know about, in order to get new insights from the model, I would like it to at least represent the things that we already do know about. And what I'm pointing out is that a lot of statistical inference is currently being developed in exactly the opposite setting, or not in that setting. So that's my primary take on it. But that's admittedly, that is a technical point, which is I can't say exactly how that impacts any particular domain at this stage. But if these things are to have impact in any kind of domain, they might not. But I would argue that at least that's a problem that needs to be resolved. Okay. Okay. So now, moving into the second part here. So statistics gets used a lot in science and in science of all disciplines, and there's something going on now. If you've read, you may have heard about, you may have seen, maybe you've even been affected by it yourself somehow. Something called the replication crisis, which is the idea that, well, as this essay in 2005 suggests, that most published research findings are false. And it turned, so this was actually, this was published in 2005 without any empirical evidence. This was just kind of a theoretical argument claiming that most published research findings are false. The argument itself,
You know that isn't
yeah. Well, this quote at the top of the slide is wrong, right? It can't be proven that most claims research findings are false. So it's at least self-consistent in some sense. But that aside, there is some merit to the argument that he gives. But I guess for those who might not be familiar with this, I guess this replication crisis has to do with the idea that. So when I was in third grade, I learned the scientific method. The last part of the scientific method was repeat the experiment. And so what's happening now is that I don't know the extent to which practicing scientists repeat their experiments, but when they publish a result, someone else will see it and try to repeat the procedures and get the same outcome that they did. If they do get the same outcome, that would be called a replication. If they don't, that's a failed replication. And what the replication crisis is that a lot of the work that's published in the literature doesn't replicate. And there's a number of reasons for it that this paper lists, or at least gives some justification for why. I'm going to focus more, not necessarily on the causes are important, but also I'm going to suggest, or at least investigate, the extent to which alternative solutions might be beneficial. So here's the empirical evidence. A few years ago, there was a study that tried to replicate 97 results in the psychology literature. They succeeded on only 39% of them. And these aren't. This isn't like you just pick anything out of nowhere. These are in reputable psychology journals. These are well-known results. There was another study in economics. They were right around 60%. That's higher, but still not so good. And more recently, maybe, and more significantly, a study just this past summer released that social science articles that were published in Science and Nature only a 62% replication rate. Now, the sample sizes here are relatively small, but nevertheless, that's an alarming number, especially given that so Science and Nature are the two most prestigious journals, not in any particular field, in science in general. And so these results are getting wide attention. When they're initially published, they turn out not to be correct, or at least they turn out not to stand up to additional scrutiny. There's a question of now, what should be done about it? I guess one question is, well, what we're doing to apply, what is the key mechanism behind these replications? And it's important to understand, without getting into detail, is that a lot of scientific fields rely on what's called hypothesis testing, and it's statistical hypothesis testing, what's called a p-value. So, without getting into the technical definition, what you can imagine is that a scientist has a hypothesis or some model of what's going on, and then they collect data to test that model, and they compute what's called a p-value, which uses probability in some way. So I don't want to say that a p-value, importantly, is not a probability, but this is a confusing thing that's best not to get into. But essentially, what a p-value does is it assesses the extent to which the data that you observed is consistent with the model that you had assumed or the hypothesis that you had made. And so if the p-value is very small, then that means that the data you observed, which is reality, is inconsistent with your hypothesis, and that's what leads to what's called a statistically significant finding. And the typical cutoff in a lot of fields is if p-value is less than 0.05, you would draw this conclusive. You would declare your results statistically significant. If it's above 0.05, you don't do that, and that's a very important cutoff because not only does it affect whether you have this label of statistical significance, it actually affects whether you get published in a lot of fields, and that's driving a lot of kind of inverse incentives in these cases. So what do we do about it? So I have a table here I don't want to get into, but there's another way of looking at this, which is to say, well, yeah, but even without these incentives, if this 0.05 p-value is just not low enough, it's not a low enough cutoff, if we did everything perfectly, we would still have a very low replication rate. And that's the argument that was made in an article from last summer. So these are the authors, and this is their abstract. And I wouldn't ordinarily, I actually didn't think about this topic until I saw this paper, and I wouldn't even have ordinarily looked at this paper, except that I saw one of the names on this list was the author, John Ioannidis, who wrote that earlier article that I mentioned on why most published research is false. That was written in 2005, this was written in 2017, so a 12-year gap. And something stood out to me, which is that this is a list of, you may recognize some names on here, you may not, but a lot of people here are very well-known names in their respective fields. And what they're suggesting is to just change this cutoff from 0.05 to 0.005. So move the decimal point over, and we'll be in a much better situation. We'll for all intents and purposes, possibly resolve this issue. And I thought that, given that we've known about this problem, and especially Ioannidis, who's pretty much made a career off of talking about this problem, we've known about it for so long, it seems odd that you could resolve such a major problem just by moving a decimal point over. So I took a closer look at the paper. I realized that I found a lot of flaws in the argument, but other people did as well. And so there were other articles. So I wrote an article myself, but there were other articles with, so there were 72 authors on this paper. There were 80 authors on this one, 50 on these. And I think that this alone kind of indicates what's wrong with how science is being done, which is that a lot of these authors on the original paper I mentioned are well-known people. And as I understand it, a lot of what was behind this was to say, well, this may not be the best solution, but by putting our names on it, maybe more people will look at it, and maybe it'll actually get implemented. And so it's kind of doing things, exactly the opposite of how science should be done. It's appealing to the authority of the authors, and many of them actually even admit to that. But the problem is that the argument itself is based on is very flawed, and it's based on a lot of hidden and misleading assumptions. One of the key things is that it actually makes a theoretical argument that assumes away the existence of the replication crisis in the first place. And so it applies the theory that is currently being violated to argue in favor of their solution and why it would make things better. And that was what I talked about in my paper here. I actually realized that you could apply their same argument, and it's quite possible and quite plausible that if this were to be implemented, that the replication crisis would actually get worse under this new cutoff, not better. So an alternative that I want to talk about is in prediction markets, and how prediction markets might be used in addressing some of these challenges in the replication crisis. And shifting gears just for a second to where prediction markets are primarily seen nowadays. So there's the current way of doing science through peer review and things like that is essentially relying a lot on expert opinion. And here's an example of an expert opinion for an election forecast. This is 538. A month ago we had the election, and about 2 weeks before that, on 538, the forecast for Bob Menendez, who was the senator in New Jersey, getting reelected was 90%, according to 538, which is kind of the authority on election forecasting. They have models, they have data, and they give these forecasts. If you went the same day to a prediction market, predicted.com, where people are betting on either side, buying shares of yes and no, a price of Bob Menendez for yes was selling for 78 cents. So what that translates to is that the market was essentially forecasting a 78% probability. Because the way this works is that after election day, if he gets reelected, the yes shares are worth $1, the no shares are worth 0. If he doesn't get elected, the yes shares are worth 0. And so in order to break even, you would need a 78% chance of this happening. So we have two different forecasts, one from an expert who's applying statistical analysis, another by, there's probably a lot of experts in the prediction market, but there's a lot of just regular people who are, having a good time or betting on some kind of hunch or something like that, just like, the stock market, essentially. And the key point is these are two different probabilities. Which one is correct? And which one is more trust? Which should we have more faith in? I guess on the one hand, you have an expert estimate saying that it's 90%, but on the other hand, the people who are in the market are able to look at that and could use that information when they place their bets in the prediction market. If this 90% forecast were correct, then the market's offering you a 12% edge right off the bat, and that is significant enough to overcome the transaction fees on this website. But the people on this website aren't buying into it. Aren't trusting that much in the forecast. So one argument is that, well, who has the more incentive to be very accurate in their prediction? Well, it's the markets, because we know how the people in the markets are affected by this. If I buy something for 78 cents that's actually worth 75 cents, I lose money on average. If I buy something for 78 cents that's worth 80 cents, I make money. The way that these 538 forecasts are assessed is actually much more nebulous and much less cut and dry, actually. But how could this relate to the replication crisis? There was a paper in the early 90s by an economist named Robin Hanson who was proposing essentially a similar idea, which he titles "Could Gambling Save Science?" And the idea is that just like we can bet on the outcome of an election, the outcome of the election doesn't affect who wins, or at least we don't, or the price of the prediction market doesn't affect who wins the election, although it could have an impact somewhat, but we don't think it does. But it gives us a better insight into what people actually believe is going to happen. And when it comes to assessing scientific journals, might we get a better signal as to what scientists actually believe about the merits of an individual paper by having them bet on the outcome? And if there's money to be made, if I know something about a paper that you don't, and I have money and there's money for me to make in the market, I should participate in the market. And so the idea, from his perspective, he argues to, instead of basing publication decisions just on the opinion of a single referee or an editor, one or two referees or editors, well, let's also take into account these prediction market prices, because these are a kind of a more stable and a more reliable indicator of what the scientific consensus is about a particular idea. Yeah.
Do you imagine that this kind of system would make it much less likely for an unpopular idea to come to the fray, so to speak?
Less likely for an unpopular idea to come.
Yeah.
Yes.
So if somebody has this awesome idea,
yes, I
but
do.
Nobody knows about it.
Yes, I do.
Yeah.
And that's, I think, a drawback to this that I'll talk about on the next page. 10 minutes. Okay.
Is there an insider trading problem here too, that the people who could be betting and then replicating?
Yeah, I mean, there would have to be some way of kind of making sure that regulating that, which automatically maybe somehow presents some issues on its own right. But I think there are drawbacks to this, and I'll talk about them in a couple slides, because I have a suggestion of my own, which is based on what I call the fundamental principle of probability, which is one of the main, if I could identify the root cause of the replication crisis, it's that these p-values are computed from probabilities. They aren't strictly speaking probabilities, but they're related to probability. And if they were, and what some people argue is that if this theory was applied correctly, then the p-value of 0.05 would mean a type 1 error rate of 5%. It would mean what it says in the textbook. But it doesn't mean what it says in the textbook once it gets written on the page of the journal for a number of reasons. So there's a disconnect between the theory, the probability theory, and the practice of probability, the reality when these probabilities somehow appear on the page of the journal. How could we make it so that the probabilities that actually appear on these pages are more, we believe that the authors, at minimum, that when the author puts it on the page, they actually believe that that number means what it's representing. It might be wrong, but the way it works now is that if I have a p-value of 0.06, I'm inclined to p-hack, or I'm incentivized to p-hack to get it to let below 0.05. That doesn't guarantee that I get published, but it certainly increases the probability, the chance that I get published. So I know that the true p-value isn't 0.04 when I submit it to the journal, but that's not what I'm after, right? So what this suggests is that, well, how could we make it so that when I report something, you can believe that, you can trust that I actually believe in that. So there's a connection in the philosophy of probability to betting rates, and if you want to actually make sure that these probabilities correspond to what the theory says, then you actually have to make that theory real and force the authors to somehow back up their claims in the same way that the people in the markets are backing up their claims. And so my suggestion is that if we're going to do this prediction market thing, the way that we should do it is, first of all, it's not a good thing to have the journals using the prediction market price to accept or reject papers for the same reason the question that was just asked. still going to lead to good ideas being rejected, bad ideas being accepted, and I have every reason as an author to try to pump up the price of my article to make it look good to the journals before they make the decision. But now, if we start the market off by having the authors actually kind of set the initial price and put money behind that, then that initial price at least will, and that initial price is the one that would appear as kind of what's backing up or what's supporting the idea that appears in the paper. Then that at least gives us a confidence that the author believes what he's saying, and the idea being that there's always going to be an information asymmetry. I write the paper, I know more than you do. No matter how much I tell you about it, no matter how honest I am, I always know more than you do. And that's never going to change. But at least incentivize that when I report some kind of metric as to how reliable my results are, that those metrics are accurate and forcing me to take into account the extra information that I have. And actually, they're likely to be conservative in this case. So whereas I tried to get a p-value to 0.04 in the past when I tried to transform a p-value of 0.06 to 0.04 in the traditional setup, in this setting you'd be inclined to actually try to inflate the p-value to make it seem like less of a, I think you would be at least, to try to make the results seem less definitive, because you actually have to offer a bet at the odds that you state. And so an 80% probability means you're offering 4-to-1 odds. A 75% probability means you're offering 3-to-1 odds. So that's, if you're wrong, you want to be wrong in the conservative direction. And so I think there's a way to possibly combine these ideas, but I do see an issue with using these market prices and these probabilities as a signal rather than as something that actually kind of, rather than just letting them serve the purpose that they're intended to serve. And that gets me to my last part, which I'll go through relatively briefly, which is just to highlight how I'm trying to put these ideas into practice now with a project that is called Researchers.one or Researchers.one. It's a website which is trying to take these ideas, a lot of the problems that are happening in academic publishing. Academic publishing is a complex system. It's not as simple as running an experiment and then reporting what you found in the experiment. There are people's jobs on the line. There is money on the line, and there is a lot of things happening that it's impossible to think about one part and to ignore the others and to still fix this problem, and that's in some way what the 0.005 suggestion ignored. It said, well, ignore all that other stuff, just make this one small fix and things will be better, not realizing that those other things that you're ignoring will react and will adjust to the thing in the same way that they reacted to the 0.05 significance level. There's nothing special about 0.05 that makes it easier to react to than 0.005. Was there a question?
No.
No. Okay. So there are, beyond the replication crisis, which affects science, there are issues that have to do with, subversive behaviors of many kinds, suppressing ideas for various reasons, and there's just the part that there's this sociological aspect to science that affects the science. In the field that I'm in, there's a journal called the Annals of Statistics, which some think is a prestigious journal. Many others actually don't. But one of the reasons why, one of the problems with it is that about 50%, about half the articles published in the journal are actually authored by members of its own editorial board. So, I'm sure that this isn't the only journal that has a similar type of a problem. So how do we correct this? And there's, of course, kind of the traditional way to do it, which is, well, to think that we have things generally correct, but we just need to kind of make them better or tighten them up a bit. The suggestion I have here is to provide an alternative, and that's what this Researchers.one actually is. So what is it? It is a real thing. It's not just an initiative that I like to talk about. It's a website. It's a publishing platform which anybody here could use. Anybody's welcome to use it, and you can publish any topic on this website. So one of the key ideas here is that we hear a lot about open access, and wanting people to be involved. But open access in the way that journals implement it isn't really open access in that it's open access to read the work. It's not necessarily open access to produce the work or to have the same benefits of peer review or whatever other benefits that the authors that publish in these journals have.
Often open access comes with an additional fee for publishing.
Absolutely.
Makes the bar even higher.
And you have to give them your copyright.
That's right.
Yeah, so it doesn't actually improve anything, but it's taken on a life of its own. It makes people, I think, feel good, and it sounds right. But I think it's been implemented poorly. But one of the reasons it's been implemented poorly is because it's trying this hedge between what might be actually a good idea, but it's realizing that we have a system in place and we want to kind of force it or tweak the system to kind of adopt this new idea. The system just adjusts, right? So here's just a sample. So there are papers published on this. We have papers in physics, philosophy, psychology, statistics, math, and so on. I checked today. I think we just started this September 1st, so it's been about 3 months, and we have about 40 or 45 articles. And so you can use it. And the key idea that I want to point out is that what makes this different from a traditional journal or a preprint server is that we still have peer review in the sense that there are many ways to get peer review before you publish, and also there's peer review after you publish. But that peer review decision isn't involved in any kind of accept or reject. There are no editors in this journal. I'm not an editor. I don't want to be an editor of anything. But I do want to be involved in peer review to the extent that it actually involves some kind of discourse of ideas and it improves things. It serves a scholarly purpose as opposed to an administrative purpose.
So do preprint servers like Archive do peer review and have accepted check?
No. Preprint server, no.
I'm missing the difference between this and like Archive.
The difference is that a preprint server is you post there and then you go publish in a journal. Now you could do that here too. You could post it here and go publish in a journal because unlike journals, we don't take the copyright. You do whatever you want with it. But this also provides, there's many other aspects of this system that I don't have time to get into now, but I'm happy to talk about. This provides the benefits of peer review so you could just publish your work here, and that's what I do. And you will get, feedback or commentary or criticism, and all that, without having to go through the hoops of submitting to a journal. And really, the peer review process there isn't intended for the author's benefit, but it's really for the editors and the journal's benefit. How many times, I don't know if you've experienced this, most people have, you get peer review feedback that actually makes the paper worse. In this case, you can ignore the peer review. It's up to you. Ultimately, when I got the idea being that when I got into this business, I thought that the person who would have the most incentive of my work being good would be me. But it turns out that that's actually not how a lot of other people think of it, which is that there's these criticisms that we get, or these objections, which is that, well, this is only going to make things worse. You're letting the inmates run the asylum. But that kind of is this. But that, in my view, is distorting the purpose of this whole system or this whole peer review process, which is that it's not primarily, we shouldn't engineer science to serve the needs of university administrators to make hiring and promotion decisions. They will make their decisions and they might have their ways of doing it, but that shouldn't be the way that the system is primarily focused, is set up to do. And that's I think the biggest difference here, which is that there's no reason why your work that's published here can't be evaluated and can't be criticized in the same way that it could be evaluated and criticized if it was published in a journal. The difference is that when you publish it here, the idea kind of has to stand on its own, right? You're not relying on the brand name of Science and Nature to say, well, that's a good paper. And so actually I think that plays into this emergence idea and this complex systems idea, which is that the criticism that this will make things worse, which we thought about for a very long time, actually I don't think that's the case, and that's not what we've seen in the 40 papers. The 40 papers that are published right now are not, from the Flat Earth Society, right? They're from reputable people, and they're pretty much they're pretty good. Papers for the most part. Why is that? Because, well, publishing there doesn't get you anything. It doesn't get you any prestige, and it certainly doesn't come with any stamp of approval. So when you publish there, you're kind of on the hook for standing up and for validating the quality. And readers know that anything that readers know that the author decided to publish it, so they're going to be skeptical. But authors also know that readers know that, and so they should take this into account. So this is, at least in my analysis of this system, in our analysis, I should have said this is an initiative I'm doing with a friend of mine who's also a statistician, Ryan Martin, who's at North Carolina State. We call this scholarly Mithridatism, which is named after Mithridates VI, who was said to have. So Mithridates V was assassinated by poisoning, and Mithridates VI was paranoid, so he ingested small doses of poison to try to protect against poisoning. And so the idea that by setting the system up in this way, we actually strengthen the literature. We could actually be strengthening the literature as a whole by shedding doubt on its individual components. And we've written about this in a number of places. And I'd be glad to talk about that more.
So, Harry, are you collecting information that you can then evaluate whether this experiment is? I mean, is the point of hosting this so that you'll have data to test hypotheses about the publication process itself?
No. I mean, data will emerge out of this, I suppose, but no. I mean, this is meant to be this is meant to be an alternative, and actually, to be used. And I use it. This is where I've been publishing, and other people have as well. So it's not an experiment per se. No. Well, it's experimental in this to the extent that it's trying out a new idea, but it's trying out a new idea not to study this phenomenon, but to actually try to, offer an alternative and hopefully a solution to it. So that's the idea behind it. Okay, so I think that I've run out of time, but I just wanted to list here several references that I've discussed throughout these 3 parts. I appreciate your questions and your attention, and I'd be glad to talk more if anyone's interested. So thanks a lot.
Thank you. It's 5 minutes over, but I mean, should probably just call it then.